All right, everybody. This is going to be the first part of the 6.3 video, which is going to talk about the binomial distribution. In the second video, we'll talk about the geometric distribution. And so we're going to take a look at a couple different things here. Just scroll down a little bit. So what is a binomial distribution? I'm actually going to answer the second question on this first, and then we'll kind of go back. So the binomial distribution is just a different setting in which we look at problems. So depending on the scenario you're in, you could have different distributions, right? One of the distributions that we can look at is a binomial distribution, which talks about counting the number of successes out of a set number of trials. Okay, it takes on parameters. So these are kind of like values you put into your distribution of n, which is your number of trials, and p, which is the probability of success. And then we got to give this some sort of variables. I'm just going to call it x, which is the values of x are the whole numbers, I guess I should say, from 0 to n, right? Because you could, if I did 100 trials, right? If I was flipping a coin, for example, a coin is like the most basic type of binomial. If I did 100 coin flips, right, there is a chance that I get all 100 heads, right? So you just have from 0 to 100, right? And there's also a chance you get 0 heads. So x can take on any values from 0 to n, where n is the number of trials. And so then it's like, well, how do we know that something is a binomial? We do this acronym called BINS, okay, where B stands for binomial. Bi meaning two, so you have two outcomes. We typically call that success or failure. Right, and success or failure can look like loads of things, right? You can talk about success being rolling, a 2 on a dice, or the sum of two dice being a 5, something like that. Okay, we talk about independence. So each trial has no impact on the next. So there's another way to think about this. It does not change our feelings. Which is I. Then we have n, which is the set number of trials. So trials are fixed. You have to know before the problem starts that I'm going to do 100 coin flips or whatever it is. And then S stands for the probability of success remains the same for each trial. So it's kind of what the binomial is, kind of just the framework for how we're going to work with this. And so what are the parameters? I wrote it up above. N and P, right, where N is the number of trials, P is the probability. And what's the number one mistake students are going to make? Not realizing we have a fixed number of trials. Okay, we are looking for counts in a fixed number of trials. So for example, if we're flipping a coin, right, we're going to count the likelihood, right? So if we're flipping a coin 100 times, right, x could take on 100 different values, 0 to 100. Okay, and we want to find the specific probability of, let's say, x being 20. Okay, so what's the likelihood we only get 20 heads when we flip 100 coins? And that's kind of what we're going to do with this. All right, so I want you to think about these three problems and think about, do they pass that acronym test? We can kind of go over this in class, but make sure you kind of take a look at this. Does it pass the BINS? So I'll do the first one and you guys can look at the second one. So the first one roll a fair dice 4 times and count the number of sixes. So the B would be, is it binomial? Yep, right. You either get a 6 or you don't. The I, independent, right? I'm going to assume that, the dice, it's a fair dice. So every time I roll it, it's going to be the same probability of success every time. And I'm going to assume that, when I roll it the first time, it's not going to change the second time. So independence is good. We have a set number of trials, 4, and the likelihood of getting a 6 remains the same at 1/6. So this one here would satisfy the conditions for a binomial distribution. So think about that for B and C. Let's look at the next problem in class. This is a good problem to think about. We'll kind of go from there. But so now, how do we calculate some of these binomial probabilities? So we have a little equation. You have the probability that x equals some number. So again, remember, x can take on any value from 0 to n. So the likelihood that you're at a specific point in this distribution is equal to n choose k p to the k 1 minus p to the n minus k. And this is on the formula sheet, which is nice. And this right here is what we call a binomial coefficient. N choose k. You kind of talk about this probably in some of your other algebra 2 classes. This is equal to n factorial over k factorial times n minus k factorial. And I want you to think about this equation a little bit and where it comes from, right? If you think about this, what we're saying is that we want to flip, let's say we're flipping a coin, and we want to find the likelihood of getting, let's say it's an unfair coin. Let's say the chance of getting a head is 30%. And we want to find the likelihood of getting 20 heads out of 100 trials, right? So that means I need to get, if this is my 0.3, right, this is my probability of success, I have 0.3 to the 20th, right, because I need 20 of those heads, and then everything else has to be a failure, right? So then I got to subtract that from 1, it's likelihood of getting a tail, and then all my other trials need to be failures. So that's where that n minus k comes from. And you're like, well, what's this term in front? This term in front is like, if we have 100 different coin flips, right? We have a bunch of these, each one of these represents a coin flip, right? We don't know where the head's going to be. It could be here, could be here, right? So we have to count the number of ways that we can kind of arrange our 20 heads. And that's exactly what a combination does. It looks at the number of ways we can do something. So the reason why we have this n choose k in front is because we got to count the number of ways we can kind of arrange our 20 heads out of our 100 trials. That's kind of the idea behind all this. And again, another problem for you to practice or try that out. The nice thing about this is there is a binomial CDF and PDF function on your calculator. It's the same place where you get all your other distributions. So you can find it there. And we can kind of look at that together in class. Is it okay to use it on the AP exam? Yes. But you still need to write down all your parameters, kind of set up the problem like we were doing in the last chapter and in earlier units. So you can set it all up, and then you can go to your calculator and go from there. Okay, how do you calculate the mean and standard deviation of a binomial distribution? So the mean, remember, we have the sum of all of our xi's. That's like your general definition is always going to work times pi. And if you actually think about this, when we start writing this all out and expanding it all out, this actually just ends up being n times p, which kind of makes sense if you think about it. If I roll 100 coins, or if I flip 100 coins, sorry, and the likelihood of getting a head is 30%, well, how many heads do we expect to get? 30, right? 100 times 0.3, just get 30. And the standard deviation of x is equal to the square root, that's a horrible square root sign, the square root of n times p times 1 minus p. And some people like to write this as q. They write this as another variable. They say this is q. You might see that. So here on this next problem, where we give you this probability, right? 18 out of 38. We're doing 10 spins. So to find the mean, just do 10 times 18 out of 38, which is 180 out of 38, which simplifies down to 4.7. And then you can do the same formula for the standard deviation and get an answer. Last big thing I want to talk about in this video, and we'll talk about some of the other stuff in class, is when is it okay to use a binomial distribution when you're sampling without replacement? Because if you think about it, normally in life, we're not going to be able to replace every time, right? If you sample from a population, you're only going to sample one person once, and then they're done. So the probability changes each time, which impacts our independence. And so what we have is we have this thing called a large counts condition. And basically all this says is that if your sample size is less than or equal to 1/10 of your population size, so little n is sample, big N is population, then you can assume independence. Then you can assume independence. Okay. And so again, because we can't assume independence always, because if I'm sampling from the classroom, for example, right, and I select one student, and now I'm not going to sample that person again. Right now the total number of my denominator is going to change, and so I don't have independence, and so my probability changes, right? And so now what I need to do is, okay, well, what can I say? Is that if my sample size is small enough, then we can assume independence. Okay? That's kind of the idea behind this. So that's it. That's kind of just the big ideas that I wanted to touch on. We'll talk about some of these problems in detail in class. But if you have any questions, let me know, and have a great rest of your day.